Okay, so for this section, we're going to keep working on optimizing functions. In this case, we're going to take some constraints um, and limit what values we're allowed to look at. So let's go ahead and jump into that. So what do we mean by constrained optimization? So we saw in the last section how to find maximum and minimum values of functions of the form z equals f of xy. So we found local maximums and local minimums, and then we also found absolute maximums and absolute minimums on a closed bounded set. So what we're going to look at now is the case that often comes up in actual practical examples where the input values of x and y aren't allowed to just be anything at all. They have some condition that they have to satisfy. So for an example of this, suppose your grade on your midterm depends upon how many new problems you're doing when you're studying, which you should do new problems when you're studying, and how many hours you spend reviewing your notes. So the number of new problems is given by p, the hours you spend studying your notes is given by n. So we have some function z is equal to f of pn, where this z is giving your grade on the midterm. However, you have other classes you have to study for, other things you need to do, so you can't just spend an unlimited amount of time each day studying, doing new problems, and studying your notes. So let's suppose we have 4 hours per day that we can spend studying for the calculus midterm. So what this comes down to then is we still want to maximize our grade, f of np, but we can only take p and n, so the total number of hours has to be equal to 4. So we're going to constrain our p and our n to satisfy p plus n is equal to 4. So this is what we mean by constrained optimization. We want to optimize the function, but we're going to constrain what values our variables can take. So this comes up super often in economics, where we have constraints on, say, the amount of supplies we have or things like that. So that we're not just looking to optimize the profit, we're going to have constraints on what goes into that as well. So let's go ahead and look at how this looks visually so we can have a good picture in our mind of what we're looking at. So suppose we have some surface here. So this is going to be my z is equal to f of xy for the first few pictures. Now obviously if I'm looking for the maximum of this function, it's going to occur up here. But that's not what we're going to be interested in here. We're going to want to constrain what our values of x and y can actually be. So let's look at some constraint here. So my g of xy equals c is going to be some curve in the plane xy plane. So in this case, I pictured it here as an oval. So my x and y values are only allowed to lie on this oval. So if we add that back into our original picture here, we can see the pink part here is the surface z is equal to f of xy, and then this purplish blue oval here, or ellipse here in the xy plane, is our constraint g of xy is equal to c. And now what we're asking for is what is the maximum and minimum values on this pink surface here where the x and y also lie on this ellipse. So we can picture that by graphing all of the points on this surface that are above this ellipse. So we see here now, we're not trying to find the maximum over the pink. This blue curve here is the curve on the surface that sits above this ellipse. So we can see as we go along this, we're above these points on the ellipse. And so when I'm asking for my constrained optimization here, I'm asking what is the largest value that's on this pink surface, but also on this curve on the pink surface. So what is the highest value this blue curve gets, and what is the lowest value this blue curve gets? So you see, it's very different than just taking the maximum value of z is equal to f of xy. It's going to be a completely different problem to solve. So that's what we're looking at in this section, is how do we figure out what the highest and lowest values on this constraint curve on the surface are. So let's go ahead and look at one more picture of how this works. So this is a different picture of a different surface. We're just using this one because it's going to be a little bit easier to draw the pictures of to kind of see what we're doing here. So if we take this surface and we look at the same type of setup, I'm going to go ahead and add a constraint here. So in this case, my constraint g of xy equals c is just a line in the xy plane. So it's just this blue line here. It looks purple, but you can see the edge here. It's actually blue. Just happens to be behind the pink or below the pink here. So just like we did on the last one, we can see what we're really looking at if I want to maximize the value of this surface subject to the constraint down here is what is the maximum value as I go along this blue curve here. So if I kept going, in this direction on the pink surface, I could get as high as I want to because this is just going to keep getting higher and higher as I go in this direction. But I don't want that. I want what's the biggest value that goes along this blue curve here. So the way we're going to solve this is we're going to go ahead and look at level curves again, or contour plots. So let's look at the level curves here. So these are the level curves, or 3 level curves. We could fill in more if we wanted, but just 3 is a good illustration here. So these are the level curves for z is equal to f of xy. So just recall that means as I go along this curve, since this is labeled with a 2, if I were to walk along this would be at a height 2 in the z direction along my pink surface. And similarly, this would be at a height 3 on the pink surface. This would be a height 4. So we're kind of going up as we go in this direction, just like we saw in the previous slide. So then I can add my constraint here. So instead of a blue line here, I've drawn it green. So this is the constraint g of xy is equal to c. And so any xy value I consider has to be on this green line, because that's what it means to satisfy my constraint. So I'm only looking at what are the maximum possible values of f along this green line. So now notice if I were to draw the level curve here, where say f of xy is equal to 2.9, notice that level curve hits the constraint here and hits the constraint here. So that means there's 2 values here in the xy plane where I'll be on the constraint and my function value will be 2.9. Similarly, you have a point here where my function is a value of 2 and is on the constraint, and is a value of 2 is on the constraint. But we also see if we go up here to 4, there's no values where my function is 4 and satisfies the constraint. So that means my true maximum value has to be somewhere between 2.9 and 4, because I can't get 4 at all, and I get 2.9 twice. So let's look at a slightly bigger value than 2.9. So if we graph f of xy equals 3, notice it still hits the constraint right here, but it's tangent. So it just hits it. If I go any bigger here, I'm not going to hit it, and if I go any smaller, I'll hit it twice. So for instance, let's go a little bit bigger to see that. So if I look at f of xy equals 3.1, notice where f of xy is equal to 3.1, it doesn't touch the constraint at all. So that means my maximum value of my function subject to this constraint can't be 3.1 because it never satisfies the constraint. So what that shows me is this level curve, when we drew it at 3, f of xy equals 3, that's the biggest level curve where we're still going to touch this constraint. Because if I move any further in this direction here, going towards the 4, I won't hit the constraint anymore. And if I move any further in this direction towards the 2, I'll hit the constraint twice. So the 3 is where the last level curve that's going to actually hit the constraint. And notice that it's exactly where the constraint and the level curve are tangent to each other. So since my constraint here at least looks like a line, it looks like the constraint is the tangent line. But if we think about this, maybe pretend that green line is curving just a little bit and it isn't actually a line, then in that case we would say, well, they're tangent to each other, so the tangent lines should be the same at that point. And that will be what the general situation is when the constraint isn't a line. So let's go ahead and formalize this now. So what we're looking for is we're looking for points A, B, where the tangent line to the constraint has the same slope as the tangent line to the level curve. And we also need not just for them to have the same tangent slope of the tangent line, but it has to actually be on the constraint as well. Remember, we're only looking for ones that are on the constraint. So these are the points we're looking for to figure out our maximums and minimums. So what we need to do then is we need to figure out, well, how do we find these points? So the first thing we can say is recall that when we were looking at curves in the plane and we wanted to find slopes of tangent lines to curves, well, we were looking for dy dx. But usually if we look at like g of xy equals c, we can't solve that for y. So in Calc 1, we did this with implicit differentiation. But we saw in this course we can do partial derivatives to give us this as well. So for instance, if I'm looking at the slope of the tangent line to a level curve of this, I can look at the partial derivative with respect to x, divide it by the partial derivative with respect to y, and take the negative of that. And that would give me the slope of the tangent line to a level curve for this function. And so what we want is we want those slopes to be equal. So if we set the dy dx equal for each of them, I'd have f of x ab over f of y ab, and the negative of that would be equal to negative g of x of ab, gy of ab, and of course then we can cancel the negatives, so this is the equation we want. We want points that are on the constraint and satisfy this equation here. Of course, this isn't exactly the form we want yet, but we're getting there. So we want to just recall the basic fact about fractions is we can have fractions be equal where the numerators aren't equal and the bottom and the denominators aren't equal. But basically what has to happen for two fractions to be equal is the numerators have to be scaled by a non-zero constant, and the denominators have to be scaled by the same non-zero constant. So for instance, we have 1/2 is equal to 2/4, because 2 is equal to 2 times 1, and 4 is equal to 2 times 2. So in that case, our lambda would be 2. So if we use that on this equation here, we can see what we're looking for, skipped it, is we're looking for this. We're looking for points where the numerator is a non-zero scalar multiple of the other numerator, and the denominator is a non-zero scalar multiple of the other denominator. So we do need this lambda to be non-zero, that's important. And then we still need the point to actually be on the constraint as well. So these are the points we're looking for, ABs that satisfy this set of equations. And then once we have this set of points, for us, in order to tell whether we have found a maximum or a minimum, we can either look at the graph of f of xy with the constraint and see whether it looks like a maximum or a minimum. It'll have to be one or the other. Or we can find points that are close to AB that still satisfy the constraint, plug that into f of xy, and see whether it's bigger or smaller than what we found. So either of those methods are valid. For this class, usually it's not going to be super complicated to tell, but in general it can be quite complicated, so you might have to actually look at a graph to see what's going on. And we saw a couple slides ago, this was referred to as the Lagrange multipliers. Well, this lambda here is what is the Lagrange multiplier, the non-zero scalar here between our partial derivatives for our function we're looking at and the constraint. So now that we have an idea of what's going on and how to do this constrained optimization, let's go ahead and work through one example here. Obviously, we'll do several more examples in class, including lots of word problems. So let's just do one with just equations here. So I'm going to look at this plane, f of xy is equal to x plus y. Now at maximum and minimum values of this plane, obviously if I was looking at the whole plane, there wouldn't be any maximum or minimum value, but I want to subject it to the constraint x squared plus y squared equals 1. So I only want points on this plane that are above the unit circle. So my constraint here is this g of xy is the x squared plus y squared, and then the c here is 1. Now we take these partial derivatives, they're all easy to take. So partial derivative of f with respect to x is 1, with respect to y is 1, g with respect to x is 2x, g with respect to y is 2y. So very easy partial derivatives to take. And now we want f of x to be lambda times g of x and f of y to be lambda times g of y. And so we want to find AB so that 1, which is my f of x AB, is equal to lambda times g of x AB, which is 2a. So 1 is equal to lambda 2a. And similarly with the y. So 1 is equal to lambda times 2b. And remember, our lambda has to be non-zero. Well, lambda 2a is equal to 1. Lambda 2b is equal to 1. So that means lambda 2a is equal to lambda 2b. Now lambda is non-zero. So we can divide both sides by lambda times 2, and this will just give me a times b. So any point that is going to satisfy our equations here, so any point that's a possible maximum or minimum, has to satisfy a is equal to b. That greatly reduces what our possibilities are. But notice all we've used so far is we've only used this condition on the partial derivatives, we haven't used the fact that the point AB has to satisfy our constraint as well. And that's an easy thing to forget when you're doing these problems, is that you have to go back and use the constraint often as well. So when we use the constraint, we know that from the previous slide that A has to be equal to B, but it also has to satisfy our constraint, which was x squared plus y squared equals 1. So if A is equal to B, that means A squared plus A squared has to be 1, or 2A squared has to be 1, or A squared is equal to 1/2. So then we solve for A, and I get, remember, A is equal to B, so A is equal to B. Since I take a square root, I get a plus or minus, and I get 1 over square root of 2. So that means my possible points that can give maximums and minimums here are 1 over square root of 2, 1 over square root of 2, and negative 1 over square root of 2, negative 1 over square root of 2. And we're going to see which is which by just going ahead and graphing our plane with the constraint. And we see here, if I plug that in, I get f of 1 over square root of 2, 1 over square root of 2 is 2 over square root of 2, because it's add these two together to be on our plane. In the negative, we add these two negatives together and we get this. And now notice if I were to graph those, the point 1 over square root of 2, 1 square root of 2, 2 over square root of 2 is this point here. And similarly, the negative 1 over square root of 2, negative 1 over square root of 2, negative 2 over square root of 2 is this point. So we can see going along this curve on the plane, this is the highest value, this is the lowest value. So this is the maximum, and this is the minimum. And that's how we solve that problem using Lagrange multipliers. So as I said, we'll do more examples in class, including some word problems, but this is how these constrained optimization problems work.